Good morning or afternoon, everyone. Welcome. Thank you so much for joining us today for a Marine Technology Society webinar. I'm Abby Wakely, Manager of Member Engagement here at MTS and your moderator for this session. I'm very excited to showcase the impactful initiatives from our MTS member, Seabird Scientific. Before we dive in, I want to kick things off with a brief overview of GoToWebinar. As a reminder, this session is being recorded. If you have any technical questions for me or questions for the presenter, kindly type them in the chat box using the tablet icon. I'll promptly address your questions or relay them to the presenters at the end of their presentations. All right, let us get to why we are all here, the webinar. Today we have a team from Seabird Scientific to discuss their new Eco V2 series and overall optical portfolio. Bailey Counts Morgan has been with Seabird Scientific for over 4 years and has an MSc in marine biology from University of Wilmington. At Seabird Scientific, Bailey manages optical products, nutrient sensors, and service. Eric has been with Seabird Scientific for almost 5 years after spending 7 years doing Arctic research in Canada. He achieved his PhD in oceanography from the University of Washington in 2012. Eric specializes in optical oceanography and also has academic degrees and professional experience in electrical engineering and software engineering. All right, thank you two so much for joining us. Bailey, I'm going to kick it off to you to take it away.
Yeah, thank you so much, Abby, for the intro, and thank you to everybody who is joining us on this webinar. Eric and I are extremely excited to talk to you all today about Seabird's latest optical innovation, the Eco V2. But first, I'm kind of just give a brief kind of overview of how this talk will go today. I'll briefly talk about our optical portfolio, then we'll dive into the Eco V2 with the overview, applications, features. I'll compare it with the Eco Classic, and then I'll give it to Eric, and he'll go over the new software for Eco V2, the science behind the technology, and then we'll look a little bit at Eco V2 data. But first, we kind of wanted to start with an interactive poll question. So for the attendees, we're interested to know if you have any experience with eco sensors before. So we're going to give maybe 30 to 45 seconds for you all to participate in the poll.
Hey Bailey, it's Abby. I am sharing the results here. We have 64% that said yes, 34% that said no, and 2% that said I'm not sure.
Awesome. Well, that's really exciting that over half of you all have used the Eco V2, or have used an Eco, sorry, not the Eco V2. And then we also have another question for the people that have used an Eco V2, what kind of applications have you, or not an Eco, sorry, Eco V2, have you used an Eco in? So I think the options are profiling, mooring, ROV, AUV, which includes floats and gliders, and then other, and if you're able to specify, please specify.
All right, Bailey, I have closed the poll and we have 50% that used it for profiling, 36% for mooring, and then 8% for other.
Awesome. Yeah, it's really exciting. Thanks for answering the polls to see kind of where customers are using our product. So really appreciate it. So now we'll kind of dive in a little bit. So like I said, I'm going to talk a little bit about our optical portfolio at Seabird. So Seabird Scientific offers many different optical instruments in our optical portfolio. We offer fluorometers and scattering sensors, which is available in our Eco V2 product line. We also offer transmissometers to measure the transmittance and attenuation of incidence radiation. We also offer radiometers for ocean color. Bioluminescence sensor is what we call our UBAT, and then nitrate in our Suna V2, and then we also offer optical oxygen sensors. But now what you all are here for is to talk about the EcoV2, so we will dive a little bit into that, but we wanted to ask one more poll question and wanted to see if anybody knows what the ECO acronym actually stands for.
All right, Bailey, I have closed the poll and majority of folks, 88%, believe it stands for Environmental Characterization Optics.
Awesome, it does. That's really exciting that people knew that. Yeah, so thanks for answering that. That is what it means. All right, but now we will dive finally into the EcoV2. So the EcoV2 offers an impressive dynamic range. This allows you to transition from all natural waters. We're also offering a 16-bit resolution and enhanced signal to noise ratio. The EcoV2 is a game changer for biological monitoring and dye trace studies. It has a robust potted optics block to ensure long-term stability. We also offer anti-biofouling technology, which you'll see in a couple slides. We also have leveraged the battery pack from the SB37 microcat product line. So if you're familiar with that, this allows the Eco to have improved battery capability and performance. Something that's also really exciting with the Eco V2 is that we are offering a 4-channel option. This kind of gives you a system and a sensor, allowing for easier and more reliable research, decision making, and predictions. It also means that you don't have to have as many sensors as you can get 4 measurements in one instead of having to have multiple to get those measurements that you were really wishing to have. So next I will show this animation. So here you can see our largest EcoV2. This is memory, battery, and an internal clock. The size is due to the battery pack that I just talked about for extended deployments. This unit also has memory and internal clock. This has titanium housing and allows it to go down to 6,000 meters. There are also numerous integration options, so these can be integrated with our CCAT 911 systems, as well as gliders and AUVs. This here shows the anti-fouling copper wiper, so you can kind of see that in motion there. Then we'll give it a little bit, and then it kind of shows there. You can see the LEDs. We also offer many different measurements: backscattering chlorophyll, FDOM, NTU for turbidity, phycocyan, and phycoerythrin. So those are just some of the offerings that you can get with the EcoV2. Sorry, I have to try to, there we go back. All right, so the Eco and Eco V2, so there's numerous applications that the Eco V2 can be used in across the world. So I'll talk about just a few of them here. So for primary productivity studies, Ecos have been used in situ to capture biological variability in primary productivity. For inherent optical properties, or what we call IOP and also CTD packages. So numerous oceanographers around the world use package systems to look at water quality and ocean dynamics. ECOs can be used to detect, characterize, and determine components of harmful algal blooms. They're used for long-term monitoring to provide water quality data. They also are used in aquaculture for dye tracing. They're used by the US FDA to determine health of aquatic environments for shellfish near affluent systems. We also offer many different turbidity options with the ECO, and that can be used for dredging. So monitoring consultants around the world have used the ECO sensors to monitor resuspended sediment near dredging sites. This is to ensure sediment does not raise to unhealthy levels for aquatic life. Many ocean observing systems use ECOs around the world, and then also for crude oil detection. So ECOs can be used to detect oil plumes, and actually were used in the Deepwater Horizon spill to detect plumes in the Gulf. So we have added many new features, but there's several that maybe would be more applicable for different applications. Again, all of them essentially are applicable, but there's just a few that I wanted to call out here. So if you use ecos for mooring applications, the extended battery life and increased data storage is really going to help you there. Then also on the profiling side, better data logging will help there as well. Again, the features that we have added is a high dynamic range. We're adding a new user-friendly software, the system and a sensor with 4 measuring options, better data logging, also user configurable output. So you don't have to request a specific baud rate for us anymore, which also means you don't have to have as many sensors. So that is also a really great improvement. And then also the download speeds have improved, which you will see in the next slide. So here is a comparison with Eco Classic. So when looking at Eco Classic, we only offered up to 3 measurements. And again, as I said, now for Eco V2, we offer up to 4. The measurement range was set, and that's when you had to, email us or interact with the sales team and say what measurement range you wanted. That resulted in more instruments for you to have to purchase, but now that is dynamic, so you don't need to set that and request that from us anymore. As I mentioned before, the user configurable output, that was not available with Eco Classic, but now that is available with Eco V2. We also store calibration info and manufacturing settings on the sensors. We have improved our optics for a higher resolution and higher accuracy. We also have standardized our angle, which you'll see in a couple slides where Eric will show kind of a diagram of an angle, and that's now 124 degrees. We have real-time data validation QA/QC. We do 9 tests for that. You can see here with the data storage increased significantly with Eco V2. We also have improved a lot of our measuring sensitivity. So here you can see the FDON measurement sensitivity has improved by 5 times, which is really exciting. The software that we're using for Eco V2 is UCI, which is a big improvement from EcoView. And then also here you can see the download speed, and that has significantly increased. So now I'm going to hand it over to Eric, and he is going to talk a little bit about the software.
So first, UCI application essentially takes you from both configuration to monitoring to visualization. So on the left pane there, you see essentially what would happen after a Eco V2 is set up with a connection. You're going to have just the monitoring statistics of its life, meaning voltage and clock backup voltage, how many free samples you have, and things like that. There's a deployment wizard that allows you to set essentially the burst size, the burst length, and how often you take those bursts of measurements. If you want to just set it up as a real-time instrument, the way ecos are used, so when it turns on, it starts collecting data at whatever 1 hertz, 2 hertz, 4 hertz, or in certain cases up to 8 hertz, you can do that. And as a result of that deployment setup, there's a PDF that is output for your records. Both during real-time operation, if you have real-time output set up, as well as if you have downloaded data, you can visualize that data. And you can see off to the right, on the right-hand side of this slide, the sensor has been queried for what essentially output fields it has available, and then you can check off the ones that you want to plot. So in this case, this was a 4-channel sensor, chlorophyll 470, backscattering at 700, backscattering at 530 nanometers, and FDOM. And we've chosen to look at just the chlorophyll 470 in engineering units, micrograms per liter. The backscattering output with 2 different calibrations that are both stored in the sensor, both for beta 700, which can lead to a particulate backscattering measurement, and as well as in nephelometric turbidity units, NTU, and then finally with FDOM. So as we see those measurements, we can see them from top to bottom. They're plotted versus time in this particular case. And this was actually just a test that I did on my own desk with just filtered water. So you can see there was no chlorophyll in the water. But you can see from the stair steps in both backscattering, turbidity, and FDOM that something was happening there with some additions. In fact, it was some kombucha, which was slightly fizzy, but also contained acetic acid, so it's just and vinegar as part of its process. There were 4 additions of that, and you can see that the backscattering and turbidity went up in 4 steps. And kind of surprisingly, FDOM went down, and that's because in certain cases, certain kinds of dissolved organic material are actually hydrophobic. And as a result of adding acid, they actually reduce their solubility. So this is a case where just a contrived case where FDOM actually went down. But you can see the resolution, particularly with FDOM, is much better if you've ever used the ECO FDOM sensor, much better. Finally, on the bottom plot was just one of the health statistics, which in this case was just monitoring the main power into the ECO V2. So here's a cutaway, or I guess you'd call it a section view of essentially any ECO or ECO V2 sensor. And the point of this slide is to tell you that the sensing principle itself hasn't changed. And that sensing principle involves essentially illuminating and detecting the phenomena in a volume. And the way that we do that is by positioning an LED, which is shown on the right, the blue LED, just to differentiate it from the detector on the left. In this case, it might be the blue LED for chlorophyll 470 illumination, and let's say a red 695 nanometer filter that would detect chlorophyll fluorescence. If it were a backscattering meter, the LED and the optical filter would match in wavelength. But the sensing principle is the same. Since we're showing this in a section view, you're seeing basically a slice through a cone. So you can imagine, essentially rotating this in 3D. So it's exactly the same sensing principle as an ECO. And I'll go over more details of that in the next slide. But just so that you know, this sensing volume has, based on work that's been done in literature, has roughly a path length of about a centimeter and a volume of somewhere between 1 and 3 milliliters. Off to the right, you can see some actual data. Now, this happens to be ECO data, but I just wanted to point it out in terms of the sensing principle. What we're looking at is a profile versus depth from 0 to 600 meters of both chlorophyll fluorescence in the light blue color and backscattering are derived from the beta 700 measurement of an ECO used in studying the North Atlantic spring bloom in 2008. And this is from the literature below. And what we can see is not only do we see, a mean chlorophyll signal, in this case, a surface chlorophyll or slightly, maybe about 50 meters or 30 meter subsurface chlorophyll maximum, but on the right in the darker trace, we can see both the mean behavior of the particles, but also the transient behavior of particles passing through that sampling volume. And those are the big spikes. And so the important thing is that this instrument is able of measuring not only sort of the mean water properties, but also in profiling mode or in moored mode, looking at dynamic behavior. In particular, for profiling mode, we can count up those spikes and take a look at how the particle transport is changing with depth. Just one note, you'll see on the bottom left, there's a note that says clearance 30 centimeters, 45 to 60 degrees. This is the clearance that we like to have from the instrument. Please point it down so that we eliminate as much ambient light as possible. Although the software does do ambient light rejection techniques, it can be overwhelmed if you point it up at the sky, and I've seen data sets that are like that. So please point it down or to the side. Next slide. So in terms of the technology involved, we've already gone over that there are 1, 2, 3, and 4 measurement sensor options. So that might be fluorescence, chlorophyll fluorescence by itself. 2 measure N might be a fluorescence and backscattering or fluorescence and turbidity if you prefer. Third is one of our most popular sensors, particularly for the Argo program, fluorescence backscattering and CDOM or fluorescent dissolved organic matter. In certain cases, you might be interested in having both chlorophyll fluorescence, phycocyanin fluorescence for detecting cyanobacteria, and the chlorophyll fluorescence will help you disambiguate the two, and finally phycoerythrin fluorescence for red algae. Next. As we mentioned, it does have a high dynamic range. So we have essentially 16-bit resolution over two different gain stages. So there's a high gain stage at 10 that has essentially a 10x amplifier in front of it, followed by a low gain stage, or preceded by a low gain stage that has no amplification. Each is digitized with 16-bit resolution. The digital and engineering value output is seamless so that you are not aware of this unless you want to be. If you want to output the two different gain stages separately, you can. The sample rate for 1 or 2 measurands is up to 8 Hertz. For 3 and 4 measurements, we're at a maximum of 4 Hertz sample rate. The next few bullet items are just to remind you again that the sensing principle between ECO and ECO V2, ECO Classic and ECO V2 are identical in that the excitation emission wavelengths for both fluorescence and backscattering and their full width half maximum, which is essentially the bandwidth of those LEDs or those optical filters, are identical to ECO Classic. So you can be assured that your data sets are seamless with respect to the parameters of the sensing principle. They both use, in fact, exactly the same silicon photodiode, so that that response is the same. We only use the 124-degree angle from which angular response function and the chi factor, which essentially turns your beta measurement, the single angle measurement, into an entire backscattering, the entire reverse hemisphere backscattering measurement. The same chi factor applies. In fact, we have the same NIST traceability as ECO Classic for backscattering using almost 2 micron beads. The algorithms used for averaging and ambient light rejection are the same. So again, you can be assured that your data sets between an ECO and an ECO V2 are compatible. Next slide. And just go back one. This is just to remind you. Can we go back one? Yeah, this is just to remind you, this is the set of measurands off on the box on the right, backscattering at 700, 650, 530, and 470 nanometers. Chlorophyll at 435 and 470 nanometers as excitation wavelengths, then fluorescent dissolved organic material, phycoerythrin, and phycocyanin fluorescence. Next slide. So again, just wanted to remind you, again, there's queryable metadata. So you can ask the sensor to tell it, who am I? What's my model? What's my serial number? What are my calibration coefficients? What was the calibration date? And so on. So this is designed much more for as a plug and play instrument. It does have output user configurable output field that has a Cartod-like QA/QC, if you're familiar with that program used in I think OOI and iOS. But essentially what it's saying is that, do I have any glitches in voltage, timing, gross range, for example, negative chlorophyll A? So if you would like that kind of QA/QC built into the output of the instrument, you can have that. And naturally, that means that the output sentence itself, the ASCII, per line output for each thing is configurable for whether you want to see counts and or calibrated values and or the QA/QC flags, voltage, and so on. You get to do it. So you can match in the ECO Classic output. There are 2 options with that. One is where it looks exactly like ECO output, except that the values now have to be 30. You have to be able to store up to a 32-bit integer for the full range, essentially up to 650,000 counts. If you want it to match ECO Classic identically and forfeit some of the 16-bit resolution, we can essentially decimate and down resolve the data into 12-bit to a range. So you could do that. The depth options are 300, 600, 2,000 meter, and 6,000 meter, depending on the model and the biofouling options that you choose. The diameter is exactly the same as Eco, so if you have a cutout in an AUV or a ROV or some mooring protection sphere or enclosure, it will fit again identically. We mentioned before the increased sensitivity in FDOM and chlorophyll versus Eco Classic. The energy that we use, particularly important for autonomous applications and moorings, is 180 to 200 millijoules per sample. To put that into perspective, that's a 50% reduction from Eco Classic, so it uses less energy. And we've got improved chlorophyll 470 traceability now using a NIST standard reference material. Next slide. So let's take a look at some data. Recently, an Eco V2 in the configuration that allows it to be deployed on a Slocum glider. This involves obviously a wet face, but a dry inner, in the case of Slocum glider, a dry inner dry science bay, and this was deployed in the FLBBCD configuration, meaning fluorescence with excitation at 470 nanometers, backscattering at 700 nanometers, and fluorescent dissolved organic material detection. And below the picture of the Slocum glider from Ocean Tracking Network is the trajectory that it took. Essentially in the upper left, not shown, is the coast of Nova Scotia near Halifax. And what we're seeing is a trajectory that started in the upper left, went to the lower right, and came back if we follow the blue around to the green and then back to the yellow. So that's the trajectory of the glider. On the right, we see a 3D visualization of the chlorophyll with depth. So each one of those profiles is a glider yaw, as we call it, but essentially a down and an up, to which we've added the color for the actual value of the measurement plotted on a log scale, which is typical for chlorophyll for fluorescence. The blue area below is just a visualization of the bathymetry. So you can see we went from the upper left in shallow water to right off the shelf and into deeper water. The maximum profile depth for this particular line is about 350 nanometers. The spaces between those profiles mean that for power conservation, not every yaw of the glider was enabled for chlorophyll as a power saving measurement. So, but near the beginning, you can see for about the first maybe few days, it was solid. So what we're seeing again is this, I call it a curtain plot, where the chlorophyll fluorescence per depth, we can see that the bright orange colors are near the surface and that the fluorometer captured a phytoplankton bloom. Along the bottom, we see essentially that same curtain, the trajectory out and then back just in the first 100 meters, and you can see that the chlorophyll bloom was pretty much present along the whole path to a depth of about 50 meters, with concentrations of chlorophyll, actually with spikes up to 33 micrograms per liter, but in terms of the average concentration up to about 9 or 10 micrograms per liter. So let's take a look at some of the other output. Here we're looking essentially the same curtain, but now we're just looking at the backscattering channel, and we can see, a little bit more detail about the sort of the particles in that bloom. And we can see that there's the concentration of particles where it's orange is closest to the surface, particularly when we look at the bottom horizontal scale versus time. And that would make sense with respect to most of the primary productivity being on the surface, as well as most of the breakdown products of detrital material being near the surface, with occasional sinking portions. Let's go to the next slide, and we're looking at FDOM. So if you've ever looked at FDOM from an eco sensor, you could see that they're at low concentrations. It didn't have tremendous resolution. In other words, you got maybe 5 or 10 distinct values. Here you can see just by looking at the color variations that there's much more definition in the CDOM. And you can see in particular the CDOM orange is near the coast. So that was probably where the bloom started, and and as a result ended, and as a result of the bloom dying, particularly through, the actions of heterotrophic protists, meaning that all those things that eat the phytoplankton and their guts spill out into the water, and that turns into dissolved organic material. And you can see as we venture away from the upper left to essentially where it turned around, the CDOM goes down as the bloom becomes younger and younger. So let's just up arrow twice and down arrow twice, just so you can see this a little bit in animation. So chlorophyll, backscattering, CDOM, one more time. Chlorophyll, again to 50 meters, backscattering near the surface, and CDOM again near the surface. Next slide.
Awesome. Thank you so much, Eric, for showing that. So if you're interested in learning more about the EcoV2, you can use the QR code here on this page. We also have numerous data sheets, comparison tables, and more at sabre.com. So you can use that code to look at our EcoV2 YouTube playlist, where we have more videos about the EcoV2. You can also reach directly out to our sales team at sales@sabre.com. But now I think we will move to questions. Again, thank you so much for attending this webinar. We are really excited to talk to you all about our new product, the EcoV2.
Hey, Bailey and Eric, thank you guys so much for the great presentation. It's nice to see all these advancements and also see it in action with Ocean Tracking Network on a glider, and great data visualizations. I love the way that it's visualized in 3D. Very easy to understand. So if anybody has any questions for Bailey and Eric on the EcoV2, please type them in the chat box. And we've actually had quite a few questions come in during your presentation, so I'm going to go ahead and kick us off. How does the EcoV2 fit into your optical product portfolio?
Eric, do you want to take that one? Yeah, I think the first answer would be the same as eco, in the sense that we provide, a number of ways to sense the biogeochemical environment. So chlorophyll is the source of all. Every other breath that you take comes from photosynthesis that happens in the ocean, and we know that primary productivity is important. Backscattering, at least at oceanic levels, can be highly correlated with particulate organic carbon. And as we know, carbon is the currency of climate change. And likewise with FDOM, FDOM is essentially, we're taking a look at essentially one of the things that we're looking at is degradation products and the age of water masses. So as we can sense that, particularly as we go deeper with a 6,000 meter option, I think there's going to be whole new territories of understanding of biogeochemical work that previously was maybe, limited to the first 1,000 or 2,000 meters. That fits in with the other products in the sense that the other optical products that we make, sense other components of that biogeochemical environment, or if you will, different ways of taking a look at the accounting problem of carbon. So whether it's oxygen, which is a result of the evolution of photosynthesis, as well as air-sea interactions, complementary to backscattering as a measure of particulate carbon is attenuation at 660. I think Gardner from Texas A&M has essentially a global correlation between attenuation at 660 and particulate organic carbon that is well established for the open ocean. So oftentimes using complementary measurements that essentially touch on the same thing help you get a better understanding. with that. I don't want to quite call it redundancy because obviously we're measuring different things, but at the end of the day, we want to have a better and more a sure understanding of the processes between sort of the particulate material in the ocean that we see and the carbon accounting that we really want to go after. Just as an aside, we make other instruments for establishing the hyperspectral absorption and attenuation of the ocean, bioluminescence, which has both, mission aspects for the military, but again, sensing for environments where certain kinds of algal blooms are bioluminescent.
Great, thanks, Eric. Another one has come in. What makes the Eco V2 different from the Eco Classic?
Yeah, no, great question. I can answer some of that. Eric, you can answer some of that too. So for the Eco V2, we offer a 4 measuring option that was not available for the Eco Classic. It's a user configurable output as well, which was not available for the Eco Classic. There's an increase in data storage and data handling speeds. We also have increased some of our measuring sensitivity as well. I don't know, Eric, if you want to add anything else to that, please jump in.
Yeah, here's a really practical thing that's very different between the two sensors. When you sat down and wanted to order an eco, and let's just say it was chlorophyll fluorescence, backscattering, and FDOM, you had to tell the salesperson what range from the ranges we had available you would have. So if you ordered a 0 to 30 microgram per liter range, if you happened to have a bloom that was 40, you were saturated. And now you don't have to specify a range. With this sort of two 16-bit ranges, we essentially cover all the possibilities, even in the most dense karst pond in the Arctic, in terms of however dense chlorophyll could be. The sensor will probably run out of light from it being absorbed by the density more before anything else. So the same is true for both backscattering and FDOM. You no longer choose a range. We have one exception to that. We do offer a separate ranging for turbidity, for high turbidity environments. The normal range is at a minimum 0 to 350, although it probably goes higher. But we also offer a 0 to 1,000 range with obviously less resolution. That's the only case where there's a ranging involved in the sales process.
Great, thanks, Eric and Bailey. And kind of along those lines, can existing Eco V1 sensors or the classic Eco sensors be upgraded to match the capabilities of Eco V2?
Yeah, that's a really great question. So we have improved the optics and the manufacturing process enough that the Eco Classic cannot be upgraded. So essentially you would have to receive an entire new head, and the head is really the meat of the instrument, and so you would need to get a new sensor. So if you have questions about that, please reach out to our sales team. We can do our best and kind of figure out a path forward for you all.
Great, thank you. And then a question on the size. Is the Eco V2 the same diameter as the V1?
Yes. Yep.
Okay, awesome. Thanks, guys. And then another question on capability. Is the Eco V2 compatible with the CR1000X data logger? And are there any special considerations for integration?
I am happy to say the answer is yes, because I personally have programmed a CR1000X, and we do have a open source GitHub site where the Eco Suna, I think an SBE 37 with a CFET associated with it, are all both individually and together integrated into CR basic programs. If you wanted to take advantage of some of the additional configurable output from Eco, for example, Eco V2, meaning Eco V2, since it stores the calibration constants, can output engineering values, in other words, let's say chlorophyll values in micrograms per liter, you would just simply need to set up the output sentence you want and modify the CR basic program to parse the values and store them in the data tables. I would be happy to help anyone first of all, find that GitHub site, and secondly, if you need additional assistance, we can help you with that.
Great, thank you, Eric and Bailey. And a few questions have come in related to the Eco Classic. Will Seabird continue to service the Eco Classic?
Yes, that is a great question. So currently, yes, we are still supporting the Eco Classic. Once we start shipping Eco V2 orders, we are going to be ramping that down. So we can provide more details about that. So please reach out to us there. But essentially, we are going to be ramping down our support of Eco Classic service. However, tech support will be available essentially indefinitely to still provide help for Eco Classic.
Great, thanks so much, Bailey. And then we had a question that I think you guys touched on briefly, but how does the power consumption compare to the V1 and V2? Specifically, my question relates to the puck styles, and maybe you can explain what puck styles is.
Eric, do you want to talk about the power consumption?
Sure. Well, two aspects. There is a version of Eco called a puck. It was widely used on, I think, the various sea glider models. I think that started out with UW, University of Washington Sea Glider Facility, made a transit through iRobot, and I think ended up at Kongsberg and finally Hydroid. And I'm not sure if it's still in production anymore, but that was one of the areas where the puck was used. So unlike the Slocum glider version, it is a wet version. We have not sold any of those for a long time, so we don't plan to provide that particular option. Some of the longer body options that can be wet will just essentially have a slightly longer cylinder than the puck does, but with real-time output, and again, somewhere between 300 and 6,000 meter depth rating. In all cases, though, the power consumption is 50% of what that puck would have been, since it's essentially a real-time, no clock, no battery, no storage option.
Great, thanks, Eric and Bailey. Is the Eco V2 sensor interoperable with the Eco V1 used in Argo floats?
I think the answer to that is yes, with a qualification. As I said, if you want to take full advantage of the range of output, before the Eco had a 12-bit A to D, so the maximum counts were roughly 0 to 40, 30 counts. And now the digital output is 0 to 650,000 counts. So one would have to make sure in the software of the float or ROV or AUV that when that value is parsed, that it goes into the integer size that matches. By some Argo integrators, that's considered a change. In other words, even though the output format, the columns are exactly the same, now the fact that a particular field can take on a range of 0 to probably more like 65,000 for oceanic values of chlorophyll, but even that is a much larger number than 4,000, just in terms of making sure that everything is solid. So that's considered by some folks as a change enough that warrants internal testing. That said, we're that close to being the same in terms of setting up the output format. The field order and names can be made identical. You just need to understand what the range of those values are.
Thanks, Eric. And some questions about servicing the Eco V2. One question came up is, how do we clean the bio wiper without damaging the interior motor?
We are in the process of developing the procedures for properly self-servicing the bio wiper. That may or may not include a tool that allows you to reposition it correctly. I'm other than, just being careful with probably an optical or what do you call it? An optical wipe for the surface with isopropyl alcohol, and then being careful to wipe off the rubber with a wiper with nothing that degrades the rubber.
Great, thanks, Eric. I love that you guys put thoughtful. Oh, sorry, Bailey, I just cut you off. Go
Oh,
ahead.
no worries. I was also going to say, I think for that question, we can reach out to you directly as well, and we can make sure to provide some information so you have that soon.
Perfect, thanks. So Kayla, Martin, please feel free to reach out to Bailey and Eric directly. And I was just going to say, I think you guys are thinking of biofouling so the systems can live a little bit longer in those harsh coastal environments. One question has come in, is the serial output data in the same format as the V1?
I'm sorry, could you repeat the question?
Is the serial output data in the same format as the V1?
That's similar to the previous way I answered, in that you have two options for setting up the output of, let's see, let me back up. There are quite a few fields, and you have complete flexibility as to what each ASCII sentence is output. So for example, for an eco, since it did not store calibration coefficients, you could never report engineering values from the instrument. That was always done in post-processing by applying the, subtracting the dark counts and multiplying by the scale factor. The firmware will do that. And if you want to output both counts and engineering units, now obviously those are new fields, and that output sentence would not be compatible with Eco Classic, but that may be what you want, and it may be worth the effort of modifying whatever your data logger is to do that. If you want it to be entirely compatible with Eco, exactly the same output sense, exactly the same range. In other words, let's say 0 to 30 micrograms per liter spread over a 0 to 4,030 count range. We have a legacy mode that when you put into that mode, it just looks and acts exactly like an eco. Now what you're giving up is the full dynamic range and the resolution enhancements that we've made. The middle ground was what, as I suggested before, you can set up the output so the columnar format is identical to Eco V2, with the exception that now the digital counts would go between 0 and possibly up to 650,000. Again, if you were in a karst pond in the Arctic, more likely in the open ocean, it's going to be somewhere between 0 and 50,000. So in that case, technically you wouldn't call that completely compatible, but I would say, the burden on the software developer is relatively small.
That's great to hear. Another kind of nitty-gritty question, will it have an analog 0 to 5V output for attaching to a CCAT?
Yeah. Eco V2 supports up to 2 analog outputs, and very nicely, you can again choose the range across which the 0 to 5, or it's actually 4.95 volt range is. Now that may contradict the earlier statement, but this is a practical reality with digital to analog conversion, which is across what range of digital inputs am I going to map to my 0 to 5 volt output, and you have your choice. So for example, if one time you wanted to deploy in super blue water and make it really sensitive, 0 to 10 or 0 to 5 micrograms per liter across 0 to 5 volts, you could do that. If you then take the same sensor and are working in a coastal environment and you want to go 0 to 50 micrograms per liter across that same voltage range, you could do that. The one limitation is there's a maximum of 2 analog outputs total. So if you have a 3 or 4 channel instrument, you can pick any 1, 2, or 2 of those. And that's, again, reconfigurable. Again, if you're out in the open ocean, you want to do fluorescence and backscattering, and you were internally wanted to then do backscattering and FDOM, for example. I'm just picking 2 different ones for sake of argument. You could do that. So again, completely flexible with respect to both the mapping of the digital range or output range. And as a result of doing that, by the way, it provides a scale factor that is then used, let's say, when you're connecting to a Seabird CTD, one of the things that you have to enter into CSAVE is what that mapping is from voltage back to the engineering units. It provides that number that you need to type in. You don't have to do any math by yourself and get it wrong, which I always do.
Yes, when it's automated, it makes it much easier. And then, so a follow-up on that question, will it use the same 6-pin cable as the V1?
Yes, identical.
Perfect, thank you. And so this is an interesting one. You guys mentioned how it can be integrated into like ocean observing systems. Can you tell me more how the sensor can integrate with different systems?
Well, it can integrate with any system that can, just like with ECO, can accept, a serial ASCII sentence output. And that is no different than from ECO, other than, as I mentioned before, what that output looks like is highly configurable. And the UCI program can help you do that. You don't have, it does have a command mode where if you want to use a terminal program and you're a command line kind of person, you can do that. But the UCI program can allow you to set up that output sentence. You just click from, it's one of those where there's two list boxes and you click whatever's on the left and it ends up in the right in terms of what you want. And then you can test that output even just through the internal plotting that I showed before, just to make sure that you're getting what you want. But that describes, again, the ASCII output sentence. And so any data logger that can opaquely log, a carriage return line feed terminated ASCII sentence can record an ECO or an ECO V2 for that matter. And again, we just discussed the analog output options that are available for the ECO V2. So if you are limited in your digital inputs, but have extra I guess on your logging device, analog to digital converters, you get extra essentially analog ports, but no spare serial ports. Again, you can support up to 2 ECO V2 outputs per ECO V2. Otherwise, with respect to mechanical integration, again, the diameter is the same. I can't remember if the length is exactly the same or within a couple millimeters, but it's not, if it's not exact, it's pretty close in terms of length.
Great, thanks, Eric. We have another question that has come in, and they're curious if you can schedule a start time.
I think that's true with the memory, battery, and real-time clock option. I'm almost positive. I'd have to double check that for sure, but I believe the sampling or the deployment wizard allows essentially a start time.
Perfect. Thank you, Eric. And we have one more question that has come in. Thank you guys so much for an interactive Q&A. What makes optical oceanography different from other types of oceanography, other than the parameters being measured?
Well, I think this comes back to what I've spent a little bit of time on, which is the sensing principle. In general, with optical oceanography, we're using some property of light. And of course, we like to control that light. So in ECO, we use LEDs to stimulate fluorescence of either chlorophyll or fluorescent dissolved organic matter or phycoerythrin pigments or phycocyanin pigments. For scattering, and so we're illuminating at one wavelength and having a characteristic of the pigment molecules themselves that fluoresce at different wavelengths. That's a property of a molecular property. That's why you can look up those, fluorescence pairs, whatever the LED wavelength is and whatever the emission wavelength, and those are well documented. There's no secrets to those. It's not a proprietary thing. It's a molecular thing. Backscattering can be made at a number of wavelengths. It's one of the enigmas of optical oceanography. What am I learning from measuring backscattering at different wavelengths? And often it is very sort of region specific in that, given a particular community composition, as that, let's say, just like we saw in the data, a bloom changes from, let's say, it starts out with the large diatoms, and then essentially as nutrients are used up, it transitions to smaller organisms. They have different scattering properties, and sometimes those are exhibited through, the different ratios or different ways that spectral backscattering responds. But the point here is we're talking about interaction of light with water. Now, we also do make radiometers, which use the sun as the light bulb. And we measure essentially both the wavelength of light at either 4, 7, or hundreds of wavelengths, which we call hyperspectral. But there's nothing magic about hyperspectral. It just means that if you've got the Crayola 128 pack instead of the Crayola 6-pack of colors. So that's the way to think of it. And we're sampling that finer, and that's where we use a light bulb. I mean, use the sun as a light bulb.
Thanks, Eric. And seeing we have 4 more minutes and we had one more question come in, I think this will actually be the last one. It kind of goes with a question on deployment. We install our ecos laying horizontally on a cement block. We orient it so the cone from the window does not receive interference from surface or substrate. Do we need to be careful with how we orient a 3 or 4 Eco V2?
The sensing principle is the same. The sensing volume is the same, since we use the same angles and pretty much the same LED intensities. They're close. So that clearance area that I showed on the one slide of 30 centimeters, that's roughly 45 to 60 degrees out. That's the maximum. That's sort of the super safe zone. I like to keep that free from obstruction. The way to tell, of course, is one of the ways to always check your sensor is to tape it over with black tape and measure the dark counts. And this measures essentially the thermal noise in the detector. Obviously, your detector cannot detect any counts less than that, unless for some reason the instrument drifts, which we don't want to have happen, but that's why we encourage you to do your own dark counts. What you can do in a case like that, if it's possible to essentially find a period where there's very little, well, if there's a way to position the instrument so that sampling, the larger sampling area, clearance area, is completely unobstructed versus, let's say, slightly obstructed, you can take a look at that and see if essentially the background counts, no matter what's in the water. If you do the 2 experiments fairly close together, you'll be able to see if for some reason you're essentially intersecting or measuring scattering from, let's say, some portion of your platform. And it's the same as if you pass your hand through the sampling volume. Of course, you would see scattering change. And so I'm mostly focusing on scattering here. That would be what you'd want to avoid, is any part of your deployment platform intersecting with obviously the closest sampling volume, but that larger clearance area. We have a handout, if you'd like, that goes over that with respect to the total clearance area, and you can contact us for that handout.
Great, thanks so much. So we are at time. I want to thank you, Bailey and Eric, for coming on this MTS webinar and talking about the Eco V2. I'm really excited to see these deployed in the environment, and I want to extend a great thank you to the audience for being so actively engaged. It was wonderful to have all these questions, and we will be sending the recording to everybody registered, and also the materials that Bailey has referenced on his slide and Eric has referenced when he was answering questions. So thank you guys again. Enjoy the rest of your Wednesday, the last day of April, and I hope you have a great afternoon. Thanks, Eric. Thanks, Bailey. Have a good one.
Thank
Thank
you,
you.
Abby.
Thanks, everyone.
Bye.